AQA tutorial on radiation, and this is the second tutorial, and it's on uses of radiation and half-life. Uses of radioactivity. Right, we can use radioactivity in medical uses, and one common use is gamma rays are used to destroy cancerous cells or sterilize medical instruments. Make sure that you actually at least know one of those uses. I mean, it's quite handy. A second use is as a tracer, where a small amount of radioactive material is used to detect things. In this case, there's a leak. What happens is a gamma source that dissolves in a liquid will be added to the pipe, and the fluid in the pipe, and it would run down the pipe. Now, it's going to be emitting gamma radiation all the time. So you would go along the surface of the ground above the pipe with some sort of detector, and you'd be picking up obviously some form of gamma radiation. But once you get to the leak, there'd be a concentration of radioactive material in the sort of surrounding soil and rock, and that would give you a slightly higher count rate, which would then tell you where the leak was. So that's a tracer. Now, why wouldn't we use an alpha source? Well, alpha is unlikely to actually get through the fluid, so it would not actually leave the pipe. Beta radiation, a beta source, again, that would be absorbed by the material in the pipe. Remember, both of those alphas only absorbed by a bit of paper or 3 centimeters of air. Beta is absorbed by a thin sheet of aluminium or a meter of air, so they just wouldn't get through the pipe, let alone into the soil. Gamma, as it's not absorbed by anything, will go right through the pipe and through the soil. Although the count rate will be reduced, you'd still pick up some gamma radiation. Okay, and there we go. So we can pick up the gamma count by an increased count rate above the leak. Another use for radioactivity, and this is another common one that's used in exams, is used for measuring the thickness of paper. If we use an alpha source, alpha will be absorbed by the air between the detectors and wouldn't actually even get through the paper, so you wouldn't pick anything up. If you used gamma radiation, well, because paper is actually quite thin, there wouldn't be a significant difference in the absorption of gamma rays, so again you wouldn't be able to tell whether the paper was thick or thin. So we need to use beta. When the paper's thin, more beta particles get through. So there's a detector which feeds back to some sort of motor system, some sort of computer controlled motor system, and that then tells the rollers to widen up, and as the paper gets thicker, more of the beta particles are absorbed, so there would be less getting to the detector, and it would then tell them to maybe come closer together to make the paper thinner. So it's a kind of feedback mechanism to control the thickness of the paper. Okay, if you can sort of be clear about how that works, and that you could describe that in an exam. Right, half-life is the next sort of main section on this topic, and it's an important part of radioactivity. The half-life of a radioactive isotope is the average time it takes for the number of nuclei of that isotope in a given sample to halve. Bit of a mouthful, but that's the way it is. Or in simpler terms, the count rate to drop to half its original value. And we'll see how that works shortly. So we've got the orange ones, which are the original active nuclei in a sample, and once they've decayed, they don't disappear, they just turn into a new nucleus. So we're not losing any particles. We emit an alpha, beta or gamma ray, but there's a new nucleus formed. So here we go. We start with, say, in this particular case, 16 nuclei. After one half-life, it's decayed to 8. After 2 half-lives, that 8 have gone down to 4. And after another half-life of 3 half-lives, it's gone down to 2. If you notice, the number of new nuclei formed has increased. And if you add the sort of orangey colour to the pinky colour nuclei, you'll find that you've got your original 16. That's quite a useful technique, which we'll use in another question. So this shows diagrammatically how the number of nuclei change. In this case, we've got 16. And you could count backwards and work out how many half-lives it was to get from, say, the 4th picture back to the 1st picture, and then work out how old something is by the number of atoms that have decayed. So it's quite a useful technique, this, and a useful idea to have in your mind about how the number of atoms drop. Okay, another way of representing radioactive decay is a graph, which we obviously use a lot in physics, and if we draw a curve, what we see is we start with 400 particles. After one half-life, we're down, so we start with 800, and after one half-life we drop to 400, which in this case is 5 minutes. 400 to 200 takes us to 10 minutes, which is 2 half-lives, because we add 5 minutes to the 5, and then another half-life, 200 to 100, takes us to 15 minutes, which is 3 half-lives. Very useful sort of graph. You should be able to draw this in the exam, and by drawing in the working out arrows, that would be your method. They would be your method marks for working out half-life. And you notice in this case the half-life is 5 minutes. It's 5 plus 10 gives us 15, and 5 plus 5 gives us 10. So the interval between each half-life is the same, which is, in this case, 5 minutes to the half-life. Okay, so you should be able to draw a graph like that and use it to work out the number of half-lives. So that's quite a straightforward one, which could occur in core or higher tier papers, working out the half-life from a graph. And the numbers are always going to be relatively straightforward. Right, dating materials using half-lives. Right, this is a typical example question in an exam. You don't have to learn what the different things are. They'll always tell you what they are, what their isotopes are. So we have carbon-14, which decays into nitrogen. Now when things are growing, like living tissues, like plants and animals, we take in carbon from the atmosphere and from our food as well, and some of that carbon is radioactive. So at some point, when in this case a tree dies, it no longer absorbs more carbon, so the amount of the radioactive carbon starts to decrease. And if we can compare that with a living sample, we can actually work out how old the particular sample is. So we've got a sample of dead wood, and it contains 25% less carbon-14 than an equal mass of living wood. In other words, it's got a quarter of the original carbon-14 that it had when it was alive. So we need to work out how long it takes for a sample of radioactive material to lose its radioactivity such that it's only got a quarter left. So I'll give you a few minutes to think about how you might do that. So pause the video, give yourself some time, and then run the video when you are ready for the solution. Okay, here's the solution. So we need to see how many half-lives it takes to go down to a quarter. Right, well, we start with the fact that when the tree was alive, 100% of the carbon-14 existed. So all the carbon-14 was there, and that starts off as 100%, or 1 over 1 of the original sample was carbon-14. 1 half-life later, that's dropped to a half, so now only 50% remains. So we've gone from 100% to 50%. That's still not 25% if you're with it. So another half-life later, a half of a half is a quarter, which is 25%. So to get down to 25% of your original starting carbon takes us 2 half-lives. Well, if we look at the first question, it was 5,600 years for 1 half-life. So we multiply that by 2 and we find that our sample is 11,200 years old. Fairly straightforward, and you're always going to have relatively easy questions like that to answer, where there's always going to be whole half-lives. We're going to go from a half to a quarter to an eighth, that sort of thing, nothing ever in between. Right, we have another typical question. This is a uranium one, and uranium decays into lead. The half-life of uranium is 4,500 million years. This is a little bit like the first example I showed you with the atoms, and as we were losing one particular element, another one was being formed. And if you can go back and have a look at that original picture, it might prove useful, or if you've got that one in your mind, you should be okay. So we've got a sample of rock where we have 1 atom of uranium for every 3 atoms of lead. So it's a kind of ratio question, 1 to 3. So how old is the rock? But if you think about it, we've got 4 atoms in this particular bit of a sample, so we'll just deal with those 4. So at the start, all of those 4 atoms had to be uranium before they started to decay. There will be no atoms of lead. So that's our 100% point. After 1 half-life, 2 atoms of uranium have decayed, and also that leaves us with 2 atoms of lead. That's 50% of the original. Right, that's not what we want. We want 1 of uranium, so we need to decay again. So the uranium goes from 2 down to 1, and if you think about it, the lead goes up to 3. Now if you look at this in all situations, we've got 4 atoms at all times. So now we want our ratio 1 to 3, which we have, and it took us 2 half-lives to get to that. So if we know what the half-life of uranium is, 4,500 million years, then we times that by 2 and we find out that our rock is 9,000 million years old. Okay, why is that useful? It's actually helpful in working out things like the age of our planet, the age of rocks that are hitting the planet, and it helps sort of determine, you know, the age of the universe and other things. It gives us ideas about how old things are. Okay, right, last little bit on this tutorial is about ionization, and it's quite an important topic really, this bit. When radiation collides with neutral atoms or molecules, it alters their structure by knocking off electrons. This leaves behind ions, which will be positive and negative. This is why it's called ionizing radiation. In living tissue, positive and negative ions can be quite damaging and can lead to uncontrolled growth of tissue cells, and we would call that a tumour or a cancer. Okay, so it disrupts the way cells grow, can kill them, which can be useful or not useful. It depends on the damage caused and how it's caused. So if we look at some various atoms and molecules, an alpha particle whizzes its way through, knocks an electron off, causes ionization, which now either kills some DNA or mutates that DNA, and that can lead to cancer. Okay. However, used in some medical physics ways, the ionization can actually be used to kill cancerous tumours. So you need to be quite clear about how we use cancer to kill and destroy cancerous tumours, but how radiation can also cause cancer. It depends on how it's used and the exposure that a human has to that radiation. Okay, dangers of radiation. So, well, as we're well aware, it will ionize atoms and molecules in living cells, and that can cause us to get cancer. Alphas externally tend to be absorbed by air and clothing, so aren't really a concern to us. Betas can travel through a bit of aluminium and certainly get inside can go through our clothing, and so therefore are slightly more damaging if we're exposed to them from external sources. And gamma rays can go right through us, so strangely can, if in controlled doses, cause little damage, certainly no more than an X-ray, but even in uncontrolled doses can actually cause quite a lot of damage. If alphas can get inside the body, i.e. you ingest a source or you breathe in dust which gives out alpha, which has radionuclides which give out alpha radiation, then that can cause a huge amount of damage to us, and alphas actually internal, if they're breathed in, are the most damaging source. So outside the body it's beta and gamma are more damaging, and then inside the body alphas would be most damaging. As I've said before, if you control how they're used, they can also be used to help us cure cancer, and are used as tracers to help see if there's any parts of the body which aren't working well. So when we're doing on uses of radiation, we need to take into account half-life, ionization power and penetration power of the radiation. There's no sort of simple solution here. It's the sort of best fit one, and what, in the end the surgeon decides. It's better for you to be exposed to a bit of radiation, and we know what the problem is, than to leave you with a problem. Typical example is a thyroid gland just below the necks, which help. If they're not working properly, they affect the way that you grow, and if your thyroid gland is overactive, it may have a cancerous tumour there, so we need to be able to kill that. So we can use something called iodine-131, which has a half-life of 8 days. That's not too long to cause damage to healthy tissue, but it's long enough to be within the body to kill the cancer tissues. It's also a beta emitter. Now an alpha emitter might be fine, but the alpha particles may not go through the whole tumour. They're only absorbed by a few millimeters of skin, or tissue inside the body, whereas the beta will go through a few centimeters of body tissue, and so therefore will quite easily go through the whole thyroid gland. Gamma rays would go completely through the thyroid gland and wouldn't be absorbed at all, so it wouldn't actually do anything. So what we need, something is that will last in the body long enough to do some damage, kill the cancer, get through the thyroid gland without causing too much damage to surrounding tissue, and in this case the best fit is the beta particle. Okay, one other thing about iodine-131 is that it is quite specific element in that it only targets the thyroid. Iodine is only absorbed by the thyroid gland in the body, so that's another reason why it's used. It doesn't expose any other parts of the body to radiation. That last point, if you can remember it, great. If you can't, just stick with half-life and the type of radiation that you need and the penetration power of that radiation. So those are the sort of points you're looking for sort of 3 marks, for a 3-mark question. Moving on to one more example. What's the best tracer for a human? Here you're given a little table of information. Technetium-99, half-life 6 hours, emits gamma rays, relative ionizing power of 1, compared to cobalt-60, half-life 5.3 years, radiation gamma emitter, relative ionizing power of 10. So both are gamma emitters, so suitable as gamma rays can pass through the body without being absorbed, unlike alpha and beta, which would not reach the detector. That's quite important for a tracer. It needs to get through the body to the detector. Technetium has a short half-life, so the patient is not exposed to ionizing radiation for too long, which would increase your chance of cancer. So 6 hours is long enough for the radiation to travel around the body, but not too long to cause unnecessary exposure. And the other main thing here is that technetium-99 is 10 times less damaging than cobalt-60, so your exposure to technetium-99 will cause less damage to your cells as well, because it is 10 times weaker than cobalt-60 radiation. So put all that information into a simple statement such as we've written there, and you'll be looking at sort of getting 6 out of 6 for a particular question. Just make sure that you use the information from the table, that you don't use words like it, make sure you write technetium and so on, so that everyone is absolutely clear what you are talking about. And you could also write the converse statements, which I haven't done, about cobalt-60, just to be absolutely clear that you've got everything written down. There's plenty of time in the exam to use all the information in that table.